Hey everybody, Josh from SILCA here with another episode of Marginal Gains TV. Today we've got coefficients and dimensionless numbers, part 2. So if you were with me for part 1, we learned that coefficients and dimensionless numbers are essentially a really clever engineering trick to avoid having to write out a million units behind numbers. You're getting into accelerations and gravities and meters per second and all these other unit things that we take. We try to take as many things as possible and kind of smush them into this one dimensionless number where all of those little units, all the little lengths and distances and everything, all of that cancels out, and you end up with this beautiful number that you can work through the math to give you accurate predictions of behavior in scenarios beyond the one for which you have just tested. So today we are talking about two aerodynamic related coefficients and dimensionless numbers that are CD, the coefficient of drag, and the Reynolds number, RE. Now, CD is a lot like the CRR, coefficient of rolling resistance, we talked about in last episode, except that CD is taking some pretty ugly non-linear things, some pretty complex things, and it's smushing them into this beautiful number that we can drop into our equation and use as a scalar that we talked about in the last episode. So let's kind of put that up here. What is the CD? So you see CD equals 2 times the drag force, right? Divided by rho, which is the mass density of the fluid that you're in. And that fluid can be water, it can be air, it could be honey, it could be oil. There's a beautiful thing that we can do here with the math to kind of make this work. So rho times the velocity squared times A, the area of the object. Now what this allows us to do, right, you take all of these things, they've all got units, right, and some of the units are squared, and it's a bunch of ugliness. You got meters and meters per second and all this other stuff in here. Those all cancel out to give us this nice, beautiful number. That number gives us something that we can now multiply times a velocity or times an area to scale what would have been, say, one test. We can now scale that to other conditions and situations. So, you think of the early days of NASA when it was still called the NACA. They were producing a lot of charts that looked like this. And this is essentially the CDs of various shaped objects. Okay, so we've got the CD of a sphere, of a square, or of a cube, of a cylinder, right, of a simple wing. What they did is they took all of these things, they're putting them in wind tunnels, they're testing them, you're getting force values data out, and then you work back to this beautiful CD number, and now anybody can take that CD and they can mathematically scale it to the scenario that they're looking at, right? So I don't need to go find the CD for every or the drag force for every size of sphere, right? I just need to find it one time, boil it back down into this CD value, and now I can model any size of sphere, okay? So not only is it making the math simpler, but it's making the math much more scalable and more usable for people, generations down the road in the future. I mean, this is a really beautiful thing that the NACA did. NASA continues this work. There's universities all over the country doing a lot of work around wing shapes and aerodynamics and surface textures and roughnesses. I mean, it's beautiful, beautiful work. And when the results are put out using coefficients, essentially, it actually becomes useful to future generations of engineers and scientists as they want to drive the technology forward. It's always great to go back and recreate the science that was done in the past, but it's also great to not have to start at zero and recreate the science of the past when you start out here. So that's our CD. CD, the way to think of that is it is the kind of the aero-ness of the shape of the thing. right, is I start with something, you know, that has say a sphere or a cube, and I want to make it faster, you know, I want to drive the CD down, and that means that no matter what the size is, the aero-ness of it will be the same. If I make you know, take a bullet, and that has a CD of a number, and then I start scaling that up, and it, you know, becomes the size of a you know, a space rocket, which in a lot of ways looks a whole lot like a bullet. You know, the CD value scales with that. Right now, we just talked about rockets and bullets, and we're talking about bicycles. Those do not all see the same type of flow. And so our CD is super critical, but we get to this other number that you'll hear bandied about called the Reynolds number. And the Reynolds number comes from ancient history. You can look it up on Wikipedia, but essentially trying to understand, Reynolds was trying to understand the transition from laminar to turbulent flow in various fluids. And he comes up with this, and this number still blows my mind. Let's put it up here. I'm not going to lie, I got a piece of paper right here because I don't actually have a screen, so I'm working from cheat notes. But Reynolds number, as he's trying to understand this transition, you've got rho, okay, so we've got mass density of the fluid. We've got V for velocity. We've got L is the length of the flow, how far the flow is flowing. And over the mu here is dynamic viscosity of the fluid. The thing that's really cool about what Reynolds discovered is that as the fluids change, right, you may have a different rho and a mass density and a different dynamic viscosity, right? So going from air to water to oil to honey, whatever, these are all changing, but the transition points and a lot of these behaviors remain the same at the same numbers. And so what ends up happening is we can take little segments of Reynolds number flow. Typically, we take them in orders of magnitude, like a factor of 10. So I might say, you know, for you know, this particular scenario, we're looking at Reynolds number flows that are on the order of 10 to the fourth, right? So, you know, 10 to, you know, to the fourth power. The flows within that are going to be pretty darn consistent. And this is where, and this is, I think, a beautiful point to make, that, you know, people come and say, hey, you guys tested in the wind tunnel at 50 kilometers an hour, 30 miles an hour. That's not me. This doesn't apply to me. Well, what we know is that at this certain kind of regime of flow, from say 20 to 50 miles per hour, there's great stability in the behavior between the Reynolds numbers seen in this range. And so actually, wind tunnel testing at 50 miles an hour is perfect for you because we can work the math and we can scale that back to be 40 kilometers an hour or 30 or 25 or 20. We are in a Reynolds regime that is beautifully scalable. Now, I just said that it's not always scalable, and that's true. I'm going to throw up, this is the CD versus Reynolds number for a sphere. And this is, you'll see this a lot in golf, gets thrown about. Because you see over here, right about 5 times 10 to the 5th, you've got this little thing, right? And we call that the drag bucket. And essentially what's happened here is you've gone from laminar flow at these low Reynolds numbers to this sort of transitional flow, turbulence with laminar boundary layer, and then all of a sudden you reach a place where the boundary layer becomes turbulent and the flow, the wake behind the ball, the pressure wake, can collapse around, and the pressure drag behind the golf ball is dramatically reduced, right? And that happens here in this pressure bucket. This is why the dimples are on the golf ball, right? So you see in this graph, we've got a smooth ball and a rough ball. And you see what happens is that the smooth ball will achieve this transition at about 5 times 10 to the 5th, maybe 10 to the 6th power Reynolds number flow. The rough ball sees that transition just before a Reynolds number of 10 to the 5th power. Why is that important? Well, you can only hit a golf ball so hard and impart so much initial velocity to that ball. With the smooth ball, you cannot accelerate it off of a golf club fast enough to get to that 5 times 10 to the 5th, 10 to the 6th power Reynolds flow. It will never get there. So, a smooth golf ball, no matter how hard you hit it, maybe goes 100 yards, 120 yards, because it never reaches the drag bucket. And so experimentally, right, you have the golfers seeing the balls roughened flying farther, and we realize that the surface roughness actually shifts the transition of the drag bucket over just enough that now you can hit the ball and land in that drag bucket of flow. The real point of this is in showing you, you've got this left-hand side of the curve, you've got over small areas, you have relatively linear behavior. So it's quite predictable. Then you get out here and you get a transitional behavior. If we were to keep going, you would see additional transitional behavior as we get towards the speed of sound, transonic flow, all sorts of crazy stuff starts to happen. But the key is to know where you are and what flow regime you're working in, and how does the behavior work in those regimes. For us in cycling, we're over here on the left-hand side of things. Actually, we're over right around here where it's pretty darn linear, and that's why I can work the math backwards to say that you, with this CD, and this A, and this CDA, and this power, are going to go this fast. It's because we have linearized and sort of simplified what would otherwise be some wickedly complex math. So I just want to say thanks to whoever in engineering decided to wipe out all those stupid units, because as every student knows, they will make your head spin. And they do that to you in school. They torment you with solving a lot of this stuff without the coefficients, and that unit thing is a nightmare. And also to Mr. Reynolds for his beautiful number and helping us understand what regime of flow we're in, so that we know if we can safely calculate and make sense of the world that we're in. So there you have it, CD and RE, two critical factors in understanding flow. We're going to be back in the next episode talking CDA. This is the one that I think is really going to land for you, where I can say, hey, let's go from that helmet to this one, and we'll change your CDA by this much, and here's how much faster you're going to go. That's where we really start to see the power of these dimensionless quantities. All right, thanks for listening, and we'll see you next time.